Hi, I'm Amanda Olson, and in this video, we are going to do a brief discussion of infinite limits and then how infinite limits apply to vertical asymptotes. So again, no rigor, no proofs in this video, no examples, just kind of a very basic overview. So infinite limits show up in one way where you are considering what's happening as x approaches a given value, let's say c, and as x gets closer to c, whether it be from the left or the right, your function outputs are increasing without bounds or they're decreasing without bounds. When that happens, you have what's called an infinite limit. So in this specific example, we're looking at the function f of x equals 3 over x minus 2. And we're considering what happens as x approaches 2 from the right. So we could make a table of values or we could make a graph, but what we see happening is that my function output values are going to increase without bounds. In fact, if I did 2.000001 or 2 and 2 and 10 thousandths or 2 and 100 thousandths or something like that, you'd see even larger and larger values. So there's not any particular stopping point. It's just going to keep growing and growing and growing, and you can get an output as large as you want. You just have to get closer and closer to that too. This becomes an infinite limit. Now, the reverse, an infinite limit, could also occur if you have something that's decreasing. So if these values were all negative, it's not the case for our particular function, but if they were, then you would have the case where you still have an infinite limit. It's just sort of like a negative infinity infinite limit. Okay. For infinite limits, they're really just one-sided. They don't have to agree from left to right. But in this case, we would then say the limit as x approaches 2 from the right of f of x, this is going to equal infinity. And then for this particular one, we can see that as x approaches 2 from the left, my function gets infinitely smaller. So its limit is a negative infinity. You can see that here. So where these infinite limits come up are when we discuss vertical asymptotes. A lot of times, if you ask a college algebra student, what is, just kind of any algebra student, what's a vertical asymptote? They might say well, it's where your graph can't, it's a line that your graph can't touch. That might be the case, but it's not always the case. Vertical asymptotes, we want to be actually a little bit more specific and more intentional. Vertical asymptotes are where your graph you're considering the end behavior for your graph, or you're considering, the f of x, sort of the end behavior. It's not just where it could actually be where your graph even touches an asymptote. So it's there's even this MC Hammer meme that says asymptotes can't touch this. That's not actually true. We're really just looking at the end behavior for our vertical asymptotes, and I say end behavior. Even that's kind of not well defined. So I shouldn't say end behavior, but we're looking at what happens to our f of x, as we get to particular values. So theoretically, I could have a function, and I'm not gonna take the time to define this, but I could have a function that has this line, and then it kind of continues back and forth until it gets really, really close to, but never actually has a stopping point that is that value. So maybe it's alternating. That could be, you could discuss an idea of vertical asymptotes, or so it's not just necessarily, or you could have a graph that, probably a more common example, you could have a graph where you have this vertical asymptote and your graph maybe goes up, and then it goes below, and then it kind of tapers, and it as you get further out, it approaches that value. Of course, that's not a vertical asymptote, that's a horizontal asymptote, but you could have that your function crosses at an asymptote. So you could have your graph touch an asymptote, and you're really just kind of focusing in on what kind of happens, end behavior at some sort of infinity, whether it be the y approaching infinity or x approaching infinity. In this case, we're looking at as x approaches a given constant, then we have y approaching infinity. So a vertical asymptote in the calculus sense, we say if f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote. Okay, kind of further definition that kind of plays more into what you would do it in a college algebra setting. You can look at where if g of c equals 0, but f of c does not equal 0, you're going to have a vertical asymptote show up. And again, I'm not going to prove this theorem, but this is something that you can expect. So just like you did in an algebra class, that idea of like, well, where is the denominator undefined that's going to yield a vertical asymptote? We still apply that, assuming that f and g have no common factors. That's like another thing that's kind of looked over. So just make sure f and g have no common factors. Then you're looking at, okay, where's the denominator undefined? And then that's where you're going to have a vertical asymptote show up. So that process still works the same. So hopefully this gives you an idea of how to work some examples. Again, I'm not going to do examples in this video, just going to kind of define what a vertical asymptote is and give you a little bit to work some limits as well. Okay, thank you.